the fact that we were able to detect a gravitational wave event from two black holes colliding 1.3 billion light years away, which means that 1.3 billion years ago, two black holes collided in space, and we were able to detect that event on the ground with our LIGO detectors. It really is amazing. And it will fundamentally change our understanding of the universe in years to come. It's a completely new window in the universe. So that's my main driver. Our scale is essentially down at 1,000 times, or 1,000th the size of an atomic nucleus. Right? So 1,000th the size of an atomic nucleus is where we're trying to detect these minuscule changes in space-time. Within the most sensitive part of the detector, what's really important are the mirror coatings, because that's what sets the limit of the sensitivity due to a source of noise called thermal noise. In materials, in any material, you have a kind of fundamental thermal noise floor called Brownian motion. There's a random motion of particles within materials. So that lends itself to understanding the atomic structure. And that's exactly what we've been doing up at SLAC. The Stanford synchrotron radiation light source, SSRL, is essentially a fantastic tool that we have. We've been able to use those facilities to get really a deep understanding of the materials. So we study these materials in such a way that we begin to understand the mechanisms, and we can suggest what materials actually may be better. So the ultimate aim, if you like, is to get a materials by design project, and that has the ability to impact the entire industry. This research, combined with the work that we're doing with our collaborators around the world, has the capability to actually be able to find that predictive element to the work. Understanding the very fundamental physics, the very fundamental reasons of why these events might happen in the universe is the main driver. And I can't think of anything really more exciting than that. The real nice thing about research is not only does it cover that astrophysics aim, but from our personal research in terms of the materials physics, we're also contributing towards the understanding of amorphous materials. We're contributing towards industrial applications. We work with industry in a number of things. A lot of the materials techniques that we're using, we can look for things that are important to optical absorption, for instance, other performance factors. And I think that lends itself to, a complete range of things that get me excited about the work that we're doing.